Hi, thanks very much, everybody who made it here to Rochester Park Hotel today. And welcome to everybody online. I'm going to give a talk. I suppose what I'll do, I'll go through the intro and you'll start to know where I'm going as we go through it. So anyway, this is me. I just have my introduction. I did that book with Abbas Gadarzi. Abbas I worked with him at General Motors in the old days. He founded US Hybrid, US Fuel Cell, and is quite an expert in heavy duty vehicles. So he has brought a lot of expertise on everything from diesel to off-road vehicles to our collaboration. The book, for those of you who know it, it's a university textbook. It's taught at many universities around the world. There is a Chinese edition that came out in 2021. I tried to integrate everything in there, and it features lots of problems and assignments, all stuff that are good for engineers. I'm currently working the second edition, and it's proving a labor of love, but the biggest challenge I'm finding in there is the battery. So about 2 years ago, I started immersing myself more into electrochemistry and battery technology, accepting that the power electronics, the machines, and everything else I was comfortable enough. And what I usually say, and on the mechanical side of things, I married a mechanical engineer from Detroit, so I do have a resource there that I can go to back in Kinsale. So there's 16 chapters in the book for those of you just in general. I'm just going to note here the chapters that are going to get significant revisions in the second edition. Electromobility and the environment, the first chapter. Really, in the last several years, we've seen Tesla and China rise to great prominence globally. Vehicle dynamics, I'm having a small bit of fun there in that I've written a whole additional material in there on Formula One and on heavy duty vehicles. That is nice, it's great for the students, and it really carries us into machines. And then batteries, which is tonight's subject, and I'll give a host of material on that. Fuel cells, not necessarily that much has changed in the last several years, or maybe you'd argue the last 50, but they are quite a solid technology. Conventional petrol, diesel, and hybrid powertrains, I'm not really going to deal with much again. Not that much has changed in the last several years, while the vehicles themselves are becoming more common. All the machine stuff, I'm largely going to skip in the second revision. We have seen BMW and Renault push more on what we call the electronically commutated electrical machine, which is like a permanent magnet machine without the magnets. And then we get into the material that I do work on, DC-DC converters. That's the power semiconductors, the introduction of silicon carbide to replace regular silicon, and that other materials there. We have charging, we have high power charging, we have bidirectional charging. So there's a whole bunch of power conversion topologies need to be looked at that have arrived in and will be coming down the line. But that is all for another day. We will discuss batteries. Now, I spent all day Saturday at a workshop at UCC with Leaving Cert chemistry teachers. There was 180 teachers there, organized by the science department at UCC. And I was, as you imagine, talking about electrochemistry. And what we're trying to do is get lithium-ion batteries onto Leaving Cert, and it will be on the Leaving Cert for 2027. And just to note here, right, so there's a revised curriculum, and we're going to note what I'm going to talk about over the next kind of hour or less, hopefully. We'll be touching on all of these. Understand and appreciate how scientists work and how scientific ideas are developed over time. Appreciate the role of chemistry in society, all batteries. Identify specific groups of elements in the periodic table. We will be going to the periodic table tonight. Stoichiometry and the mole. We will briefly talk about what the mole is. It's quite a fabulous concept. We couldn't discuss chemistry without discussing combustion, and it takes us back to why batteries go on fire. So we'll have to discuss that. It's a fun topic. Equilibrium constant, we won't touch on that, but it's a lovely part of chemistry as well. We talk about what are primary and secondary cells, the cathode, the anode, the electrolyte, we will talk about plenty. The hydrogen fuel cell will be on the new curriculum. I won't be discussing that tonight, but that's another good discussion for an hour. The last one there, we'll briefly look at lithium-ion cell operation, mining, disposal and recycling. We'll talk about some of those topics. So the presentation we're going through tonight, we're just finishing the introduction. We're going to go through history. We'll do some basic definitions in electrochemistry. We will start to put chemistry, the elements, the operation, and some equations together. We will talk about energy, capacity, and that'll carry us into stoichiometry. Nice chemistry word. I didn't know what it was before 2 years ago. Now I know. We'll talk about car batteries. We'll talk about lifetime aging and safety. Briefly on charging. We'll talk about the resistance of a battery, which is a good topic. And in the world of chemistry, that's called kinetics. And we will then we'll end up with the lithium sourcing and disposal. So when we're talking to leaving certs, we're supposed to start with a story. So way back in around 2015, 2016, I started to realize that John Goodenough, the character here in the screen with myself, with more here at the time, had done some great work in lithium-ion batteries. And I decided to contact him. I read somewhere that he was in his mid-90s, and I was pretty sure that he must be dead. But I Googled, I couldn't find an obituary. I found an email for him at the University of Texas in Austin, and I sent him off an email. And about 2 hours later, he replied to me. And I was a little bit ashamed because I never respond to students with anything in 2 hours. So John Goodenough, fabulous character. We'll talk about what his contribution to the battery was, and it's huge. This is we took this in San Antonio in Texas in 2019 or 2018 when we were doing the book launch. So anyway, John finished. John was, I think he went to Yale. He was into maths and physics. He was in the US Army. He was in the weather service for D-Day and all of that. And then when he came out the army, he got demobbed. He went to the University of Chicago. He told the professor that he thought he could do great things in physics, and the professor responded, "Don't you know that anyone who has ever done anything significant in physics has already done it by the time he was your age?" John is credited with inventing his version of the lithium-ion battery when he was 57 in 1979, 1980. But so anyway, I sent John an email saying, "John, I'm writing this history, I'm doing the book. I am saying that you invented a battery, and do you have anything to add?" I was kind of half expecting him to come back and say, "Oh, don't forget Paddy Murphy from Kilmurray and Noel Barry from the city." He didn't. So fair enough. But when we go to 2019, October, November, the Nobel Prize was awarded in chemistry to 3 characters. John Goodenough on the left here, Stanley Whittingham on the right, and Akira Yoshino on the left in Japan. Now, we'll talk about what all their contributions were in the next couple of minutes. So, but first we'll do a small bit of chemistry. Just to note here, the very first word in the left is Volta. Volta is credited with creating the first battery. And what happens in a battery is we need 2 metals, dissimilar metals, and an electrolyte, something with salt in it, and then we can get a voltage created. That was his basic discovery. He built on what Galvan had done. When I look at, does this have one of those shiny things? Oh, it does. Does this go on the computer? Probably not, right? So when I look at what we have here, we'll be looking at the cell a little bit more, but very simply, we're going to have, when we discharge, all the way over here, when we discharge, current is going to come out of the positive terminal and go into the negative terminal. Electrons are going to come the other way, and ions are going to come from the cathode. They're going to come through the electrolyte, which is all filled in here as liquid, and make it to the cathode on the other side. And in between the screen part is a separator. So we talk about discharging the cell, that's pulling current out of the positive terminal, and charging the cell is to push current back into the positive terminal. So we'll touch on these a little bit more. Okay, so our basic definitions. Electrochemistry is the study of the relationship between electricity and chemical reactions. Oxidation and reduction are the basic reactions. A voltaic cell or electrochemical battery cell is composed of 2 half cells. So we always talk about half cells. The cathode is 1 half cell, the anode is the other half cell. In the world of chemistry, they will often only talk about half cells, but in the world of engineering, we need to have 2 cells to get something done. So at one cell we get oxidation, and at the other cell we get reduction. Oxidation, we'll come back on what these are. And then our electric battery is when we have one or more electrochemical cells, and that's going to produce direct current. The anode. The anode is a solid metal connection, that'll be over here, negative terminal, within the battery at which oxidation occurs during discharge. The anode is the negative terminal of the battery. So there we have over there. The cathode is on the other side. That is going to be the solid metal connection or electrode at which reduction occurs. And that's the positive terminal. The electrolyte is a substance that's a liquid or a polymer that's going to fill in the gaps. Everything is porous here. And it's going to allow the flow of ions within the cell itself. So as we just looking at this, as current comes out from the positive terminal, electrons are going in. If electrons are flowing from the negative terminal to the positive terminal, for every electron that flows, a lithium ion must cross from the anode to the cathode. So it's very simply, they must mate at the other end. And that's what creates our circuit in there. A primary battery is a battery which one or more cells in which an irreversible chemical reaction produces electricity. So that could be your alkali manganese, the battery that you kind of buy in the shop, you discharge it and then you recycle it somewhere. And a secondary battery is your lithium-ion battery, your car battery, your home solar battery, your phone battery, secondary battery which can be recharged repeatedly. Definition, we talk about state of charge. State of charge is the proportion or portion of the total battery charge that is available for discharge. That'll pop up as a definition. So that's one way of looking at it. For 100% charge, the battery can give us all the charge. We can also like to use depth of discharge. That's the portion that has been discharged. So it's kind of, it's the inverse of the state of charge. Sometimes it's nice to use depth of discharge. So when we're 100% depth of discharge, the state of charge is 0. And then we talk about the state of health. The state of health is basically when we make the battery is going to age. And what do we have initially? And then what are we going to have later on? The simplest parameter to measure is the capacity. But we have resistance, we have capacities, a whole bunch of parameters can be measured. So our state of health is capturing really the degradation of the cell with time. Okay, we're on to history. So Galvan is credited with demonstrating a relationship between, I suppose, electricity and muscles and actions within the body. But Alessandro Volta, I think it was in Bologna or somewhere in Italy, he invented what they call the voltaic pile. And the voltaic pile, he had all this bunch of discs of zinc and copper, and he separated them by cloths soaked in brine. And this was really the first battery. And we see Volta here meeting Napoleon, which I think was around 1803, or actually, I got to think about this. Before Napoleon went to, where did he go? Elba. He certainly would have met Volta. Then as we go on, we had, for much of the 1800s, the battery was the source of electricity. This was to change in the late 1880s, 1890s with the work by Westinghouse, Tesla and Edison, and the development of full AC and DC systems. But what I kind of note is when we look at the battery, we have copper, we have zinc. When we look at electricity, we have iron, we have copper as well. The ability to work with metals had really developed. And we were using those technologies in the 1800s to get us electricity and other forms of motion like vehicles and the internal combustion engine. They all developed in this time. 1859, everybody who drove here has a lead acid battery in their car, the 12 volt. That essentially was invented in 1859 by Gaston Planté. It hasn't changed that much in the last 100 and something years. The dry cell, what we call the dry cell, is our rechargeable battery or alkaline manganese that we have, our basic AA, AAA. That technology was invented in the 1860s by George Leclanche. So these are old technologies that we have refined significantly with time. Then Edison came along. Edison sort of invented the light bulb, or he worked his ass off to get the light bulb working in a format that we'd be able to use. Just a brief phrase here from Edison, 1883, he said he was going to solve the battery, and once he solved the battery and he had the DC power system, the electrical problem was going to be resolved. The storage battery is, in my opinion, a catch-money, a sensation, a mechanism for swindling the public by stock companies. I'll just scroll down. Just as soon as a man, and it's all men in this audience, gets working on the secondary battery, it brings out his latent capacity for lying. So that was 1883. Edison looking at the battery and kind of running into a dead end with it. Now, to be fair, in 1899, Youngner invented the nightcap battery, which served us well again for 100 years. And Thomas Edison filed patents on the nickel-iron battery in 1902. So there was a lot of work going on there. So that was when nickel started first preparing batteries. Lithium. The element lithium was discovered in the early 1800s in Sweden. It was named for the word stone, lithos. It is the lightest metal. It has the highest electrochemical potential. It is very reactive, especially with air and water. And from the early 1900s, it has been researched as a possibility for a battery. The lithium battery as we know it came by in the 1970s, or little, what's called our coin batteries, or CR2032. Those are 3-volt batteries. Now, what I note here, the anode in those batteries, the anode in those batteries was solid lithium metal, and we call that elemental metal. And that's a key difference from our lithium ion. And then the cathode was iodine based. And then we had a lithium salt electrolyte that was allowed the ions to flow back and forth. These cells were developed for pacemakers in the 1970s and have also served us well. And we have variations of these cells today. So lithium. Lithium is the third element in the periodic table. The first element is hydrogen. Just in case it comes up later, we also talk about sodium-ion batteries. And you'll notice there that sodium is the 11th element on the periodic table, and it's just below lithium. So what happens is a lithium atom is, I suppose, very reactive. It's very happy to give up an electron and become a positively charged ion, which we call an ion. So what were all these folks doing, right? So Whittingham, right? Now this is very counterintuitive. But Stanley Whittingham developed the first rechargeable lithium-ion battery while working for Exxon or Esso in the oil business in the 70s. So it's not where you expect us to develop. And to be fair to them, they worked hard to develop this battery, but we see the reasons why it wasn't going to fly. And they eventually kind of had to give up on the business. But it set the ball in motion. The Whittingham battery is as follows. The anode is this solid blue material here that was solid lithium, elemental lithium. And then the anode, the cathode, he came up with a great idea for the cathode. Instead of this iodine-based cathode, he said, what if we had a cathode there that could house or host the ions? And the word we use there is intercalate. And he used a titanium disulfide to intercalate or host the ions as they go back and forth. So it was a great battery. He solved a serious part of the problem with his intercalation approach. However, he was only getting 2 volts out of the battery. It was an extremely reactive battery. And why was it an extremely reactive battery? If we go over here to the right, so if we have solid lithium in the anode, as we do, especially for high power charging, as we push the ions through the electrolyte from the cathode to the anode, it doesn't all neatly gather along the surface of the anode. We get these like stalactites and stalagmites. We get these dendrites, we call them, that end up poking through the electrolyte, coming through the separator, shorting into the cathode. And as we'll see, all hell is going to break loose when we do that. So the safety, the fire issue was a big challenge for these batteries. So that's their elemental lithium. So then we come to John Goodenough. John Goodenough kind of took us on our next step here. So he kept the solid elemental anode, but he replaced the titanium disulfide with cobalt oxide. And this was a far better material to use to host the ions. The challenge, or well, the great thing, so the big benefit here is this battery got up to 4 volts. And you can measure the energy capacity of a cell and its efficiency by really the voltage it can get to. And 4 volts was a fabulous level. Now we had something to work with. Because the lead acid cell is 2.1 volts. Nickel metal hydride is about 1.2. I'm not sure what NiCad is. It's probably low as well, like nickel. And the manganese, the rechargeable cell, or the primary cell, is about 1.5 volts or 1.6 volts. So anyway, John solved this chunk of the problem by going to 4 volts, but we're still left with this issue on the anode. And then that's where Akira Yoshino came along. He kept John Goodenough's cobalt oxide on the cathode, but he says, okay, what if we intercalate on the anode? So he took the anode and replaced it with, I showed this graphite here, but petroleum coke. And that was a graphite it's a carbon-based structure, a lattice-based structure, and it then would intercalate and host the ions at the negative terminal. So now we almost had the perfect battery because we got rid of the elemental lithium, which was a fire hazard, because we couldn't control. It's fine for a primary cell because we can pull the ions out. We're not putting them back into the anode. When we're putting them back in, we're going to get the dendrites form. And with the graphite there, or the petroleum coke, we weren't going to have the dendrites form. So this became the battery that we kind of know of today. Sony was the first to commercialize in the early 1990s for, I suppose, laptops and eventually phones. Tesla were the first to put on a car in 2008. I do remember Nissan working on a sodium battery in the 90s on EVs, but I don't know what technology they had. The anode shifted to, is still carbon-based, it shifted to graphite from petroleum coke. And we will be seeing that we have shifted from pure cobalt, which is very volatile battery, to also include nickel, manganese, and other metals. Probably one of the most important batteries we have goes back again to John Goodenough. So John Goodenough was never convinced about the lithium metal oxide battery. He wasn't convinced about all this cobalt in there. He thought it was all too volatile. He kept working this, and then in the mid-90s, he came up with the lithium iron phosphate, or the LFP. And some of you who came here in electric cars will be driving an LFP battery. And the inventor for that is really John Goodenough. It's also, if you have solar power at home, that is going to be the battery that's in your solar installation at home. It's a far safer battery. We're going to see why as we go through this talk, why it's far safer. And I expect on the large grid batteries, I presume they're LFP as well. Or I know some of you here work on grid, but I expect they're LFP. So I don't have too many equations here, but a small bit of chemistry. We're looking here at the discharge. Okay, we just look at the diagram because we like pictures. So our cathode, now we've talked. So what I show here as these little bubbles, those are metal oxide arrays. Could be like, simplest would be a cobalt oxide, which for every cobalt, we'd have 2 oxygens. So it must be the smaller ones on the metal. I know it's in the small printer somewhere, and I did make the drawing. And blue are the ions, which we're saying are going back and forth. And then in the so on both sides, we're in our basic cobalt technology. Just to note, the ions are kind of stored in layers within the cell. We'll explain why that's important later. Whereas for the graphite, they kind of work their way into lattices and get stored in the anode there. So our standard for discussion in electrochemistry, because when we're charging, the other terminal is going to be reducing, and first one is going to be oxidizing. So the basic convention we have is during discharge, we get oxidation at the anode, and we get reduction at the cathode. And that flips, but that's our convention for these. So now we look at we look at our equation here. At the cathode, we get, actually, I'll go to the anode. At the anode, we get oxidation. So this lithium carbonate is going to break down to become graphite, C6. So LiC6 is lithium carbonate. Graphite, break down to graphite and release the lithium ion and release the electron. So this is where we're going to get the oxidation. We're going to lose electrons. Those, and then we're going to get a voltage, a half cell voltage induced there of about -3 volts. So we're achieving the full electrochemical potential of lithium by getting 3 volts from a terminal. Then, so that's all happening at the anode. The ions come across, so we see at the cathode, the lithium ion is going to come straight across through the electrolyte, through the separator from the anode to cathode. The electron is going to go outside and do all the work. And the two of them are going to combine with the metal oxide, which could be, we say, cobalt oxide, and we get lithium metal oxide or lithium cobalt oxide. And at that half cell voltage is going to be 1 volt. We subtract the two from each other and we get an overall cell voltage of 4 volts. So that's, and that's pretty much as high as we can go. Well, I'll put a caveat on that. But that's we're achieving the full potential of lithium, and the only thing above lithium is hydrogen. And we're only using that in fuel cells. So this is what we talk about when we describe the operation of the lithium-ion cell. It's like a rocking chair. The ions rock back and forth as we charge and discharge the cell. Oxidation, reduction, flip terminals as we charge and discharge. So that's just our sketch here. But if we look down here below, we see a characteristic here. Now, this is for, this is for a lithium, a LFP cell. Just looking at the voltage, it's about 3.2 volts. But what we see is this is state of charge in the bottom axis. When I'm 100% charged, we're going to get the highest voltage. We're going to get 3.3 to 3.4 volts. And then, so when we're 100% charged, all the lithium is going to be the little blue dot here, and that's going to be in the anode. As we do a constant current discharge, so we constantly remove the lithium, constantly remove the current, the amount of lithium is going to reduce in the anode, and the amount of lithium is going to increase in the cathode, and the voltage is going to reduce. This relationship can easily be described by a log relationship. So when fully charged, the voltage peaks up, and when fully discharged, the voltage starts to sink down. So this would be characteristic of what we call the Nernst equation. So our battery structure is as follows. So we've talked about most everything here. So let's introduce a couple of new terms. In the very first charge of the cell, when we make the cell, we have this nickel manganese cobalt powder. We're going to mix that with lithium and mix it with a binder. So we're going to have all the lithium in the cathode initially. And then when we go to move the cell, we're going to have the lithium move from the cathode to the anode. On the very first charge of the cell, we're going to get a very thin layer that's going to form on the surface of the graphite. That thin layer is actually very useful because it protects this graphite structure. Graphite is just like the lead in your pencil. And it's going to fracture, it's going to break. So now we're putting a very thin layer of lithium on the surface of it. We call that the solid electrolyte interface. It's what we call a passivation layer. It's formed in the first charge. And it takes about 7% of the total lithium that's going to be in the cathode. And it's kind of stuck there permanently. It's going to add resistance to the flow of ions. It's going to grow with time and cycling. It's a source of aging in the battery. And its thickness, it's about 30 to 100 nanometers thick. It's quite thin, but it has a fundamental role. So I showed this as the cathode as a nickel type cathode with these layers. So the lithium ions are going to be stored intercalated in these layers. We need to retain about 10 to 20% of the lithium within the cathode in order to basically hold up the structure. If I fully discharge the pack, move all the lithium out the cathode for this type of cell, the cell will die. So we always keep, probably in a modern cell, maybe about 10% back, but it used to be a higher number in earlier cells. And then I just note here that the electrolyte, so this is porous on the cathode, this is porous on the electrode. The separator between them is a polyolefin, it's porous. And what we do is we pour in liquid electrolyte. And that is just a little, there'd be a ethylene carbonate, and then there's a lithium salt in there, lithium hexafluorophosphate. It's a long word, but it's LiPF6, I think. So there's a whole bunch of components in here, and we'll see what that means as we go through the chemistry a little bit more. Yeah, I'm just looking there. The carbon is going to be the very small, oh, sorry, the carbon is here, just all the carbon, this black parts. The metal, the cobalt here is the smaller dots we see there, and the oxygen are the larger dots. So we get 2 oxygens for every metal. So when we talk about chemistry, just to briefly touch here, a common technology that was used by Tesla in the Model S would have been cobalt has got a bad reputation. It's also quite expensive. So we talk about nickel, cobalt, aluminium. That's 85% nickel, 10% cobalt, 5% aluminium. And we can write it in any form where we maybe put a subscript as to what proportion of the metal is in the cathode. Another way of using it is we describe the cathode as being NMC 111. So it's 1/3 nickel, 1/3 manganese, 1/3 cobalt. A commonly used technology now would be NMCA 6111, 60% nickel, 10% manganese, 10% cobalt, and 10% aluminum. Small bit more chemistry, periodic table. This won't be too bad. Okay, so hydrogen, just under hydrogen is lithium, and just under lithium is sodium. But we're mostly all about lithium. The other element over here, carbon, is our main element in the anode. We can dope it with a silicon oxide, and we see that silicon is just under it, so that adds to energy density in the cathode as well. And of course, we got oxygen over here. That's what we call a ligand. So we started off here in John Goodenough's world with cobalt. That's the 27th element in the periodic table. And we mixed that cobalt with nickel, which is right next to it, manganese, which is a couple of elements before that, and oxygen, which we call a ligand. And so the oxygen really allows us to form these complex bonds with these metals. I can replace these other metals with iron, and that would be 1 iron with 4 oxygens for every 1 iron. So that adds to weight and stuff with the oxygen. We call these metals here, those are the transition metals. They're I think the d orbital elements in the periodic table for those of you really into chemistry. And the other thing there is aluminum or aluminium is over here. That's kind of a post-transition element, but it acts to stabilize the other elements on the cathode. Okay, we'll go to the easy math. In our world, the unit of energy is the joule. Named for James Joule, whose first occupation was he was a brewer. And then we move on to James Watt, and the unit of power is named for James Watt. And of course, he invented the steam engine and did the first control. And just to note there, 1 joule of energy is 1 watt for 1 second, but that's a very small unit of energy. So 1 watt hour is 1 watt for 1 hour, 3,600 joules. But what we like to use in our home and in our cars is a kilowatt hour, which is 3.6 megajoules. So that's the first thing. Now we're going to put together the energy with the chemistry. In the SI system, charge is measured in coulombs, named for a Frenchman. Current is measured, is the flow of these charged particles, and that's named for ampere, also a Frenchman. So 1 coulomb is 1 amp for 1 second. 1 amp hour, which is what we often use for batteries, is 1 amp for 3,600 seconds, and that's 3,600 joules. So amp hours is the term we use to describe the capacity of a battery. So we'll continue further. But certainly in car batteries, we tend to talk about watt hours. So what we do there is we take that capacity, which is amp hours, we multiply it by voltage, which is volts, and that is going to give us watt hours, because volts times amps is watts. So then we're looking here at a 18650 cell from probably Panasonic. And that is a 3.4 amp hour cell with a 3.7 volt volts coming from it, or 12.58 watt hours. So that's all kind of straightforward. So the amp hours you're going to see on your cell, you buy your car, you're going to see your watt hours. So now we're going to go to the mole. Now I must study a small bit more in the mole, but let me give you a small bit more chemistry again. The atomic number of an atom is the number of protons in the nucleus of the atom. And this is the most amazing number. Avogadro's number is the number of carbon-12 atoms in exactly 12 grams of carbon-12. So carbon-12 is a nice stuff. This value is approximately 6.0229 by 10 to the power of 23. It's a big number, fabulous number. It's as big a number as I've come across in my world. A mole of a substance is defined as Avogadro's number of molecules of that substance. The relative atomic mass is the mass of an atom or molecule relative to 1/12 the mass of carbon-12. 1 coulomb of charge is approximately 6.242 by 10 to the 18 electrons. And I think if we flip that over, it's 0.16 something by 10 to the minus 19, which is something you'd learned, I think, for the junior cert in first year engineering. So just to look at what's here, lithium is the third element in the periodic table. It's got 3 protons, 3 electrons in the outer orbit, and it's got a relative atomic mass of 6.49. So therefore, we'll have 1 Avogadro's numbers worth of lithium atoms in 6.5941 grams of lithium. And same way in carbon, we'll have 12 grams of carbon will have Avogadro's number of carbon. So those are our basic numbers there that we've seen in junior cert and leaving cert, and they're fabulous numbers. So let's put them to work in our next slide here. So the basic Tesla vehicle has a cell, I should have brought some, which is about the size of my either thumb or first finger. It's 18650, it's 18 millimeters in diameter and 65 millimeters in length. The basic storage in that Tesla cell from Panasonic is about 3.4 amp hours. So now let's put all what we've just learned together. 3.4 amp hours is 3.4 amps for 1 hour, 3600 seconds. So it's 12,240 coulombs. The total number of electrons there, we multiply by the number of electrons in a coulomb. And we're going to get 7.46 by 10 to the 22 electrons. And that is a very long number. And as long as I've written. So the number of moles, we'll get this right now. We can pull out 3.4 amps for 1 hour from this pack. Or we can pull 1 amp for 3.4 hours. It's a constant. So the number of electrons that come out when we do that is this 74.6 by 10 to the something electrons. So now, how many moles is that? Well, we divide by Avogadro's number, and it's simply 0.1239 moles. It's a very small number, very small weight. And look at all the electrons coming out. Think of all the electrons in your cells. The active lithium, so we take the number of moles, we multiply it by its relative atomic mass. There is roughly 0.86 grams of lithium in that 18650 cell. So if I go to your Tesla Model S 2023 car, there is let's go here. We have, what do we have here? Energy. So we had in our 18650 12.58 watt hours. In our Tesla Model S, we have 100,000 watt hours. That means we're going to have 110 cells in series. We're going to have in series with each one of those cells is 72 others for a total of 7,920 18650 cells, each of which is about the size of your thumb. I'll multiply, so that means we multiply this, it's almost 8,000 by the amount of lithium we have in each cell. We're going to have about 6.8 kilos of active lithium moving back and forth from anode to cathode and cathode to anode when we fully charge or discharge the cell. Just on the voltages, we multiply by 110, we're about 407 volts, and we can multiply by 72 to get the total amp hour capacity of the pack. And the weight of the pack Our single cell was about 48 grams, and the pack itself, by the time we scale it up, is over half a ton. So I told you we talked about cars. We're finding out the cars. So here we see the Chevy Bolt. I worked on the General Motors EB1 for 10 years. That died. The first electric car that GM came with next was them, the Chevy Bolt. Now they have a massive line of cars out now. They have the new Cadillac Lyric. My sister-in-law just bought one, and someone else I know just bought a Chevy Equinox, I think. So they're pushing hard and actually very close to making money on EVs, which is a big step in this world. So here we see the Chevy Bolt. It was basically a little a mini SUV. It would be a crossover vehicle is what we call today. And here we see at the very bottom here, that's all the battery pack. And then in front of it, we got the motor and everything else that goes in there. So the battery pack was all this blob. We'll be looking at it more. This is what the battery pack proper looks like. There was modules on top and modules on the bottom. So we have 10 different modules in there. And we look at the other components that are in there in a few more slides. So other vehicles, this is just the work I do in the classroom. We assign each student a car to research and look at. We have here the Tesla Model 3 rear-wheel drive. Below that, we have the Hyundai Kona, both very popular cars in Ireland. At the top, we have the BMW iX Drive 50, and below that, we have the Ford F-150 Lightning. I haven't seen that in Ireland at this point. I'm not sure if they're here. So when we, just to note, when we do these automotive batteries, we're going to have a lot of cells. We're simply limited by chemistry that we can't have more than 4 volts in a cell. Now, those of you in the power industry know that we need to get as higher voltage as possible in order to minimize the current, minimize the amount of copper, and maximize the efficiency of the system. And that's true whether it's electric vehicles or whether it's high voltage grids. So if I can only have a 4-volt cell, then I'm going to start adding them in series. So then what we know, we say 3S, so 3 cells in series. I may also add cells in parallel. So in series will give me more voltage, in parallel will give me more current. So we'd say 1 in series, 3 in parallel, but in our cells, we will tell to add them both in series and in parallel. So in this case here, we have 2 cells in series, and there's 3 cells in parallel for each of those cells. And so this is a great website for those of you into cars. This is the EV database. It's either based out of the UK or Holland, and they compile in information for years data on all these cells. It's really cool. So just looking at the Tesla Model S, they will tell us this 2023 vehicle that it will do a 0 to 60 acceleration or 0 to 100 kilometers per hour in 2.1 seconds. It's fast. Top speed is 282 kilometers per hour. It's about 180 miles per hour. So the range is 560 kilometers. The nominal capacity of the pack is 100 kilowatt hours. The battery is lithium-ion. The number of cells is 74 times 110 or something like that, 7,920 cells. The 400-volt architecture, Hyundai and Kia and Porsche would be using 800-volt architectures. The total power is 760 kilowatts. Yeah, this must be all-wheel drive. Just over 1,000 horsepower. Torque, it doesn't, yes, of course it says all-wheel drive. Now, we'll briefly touch on this. We can't use all the battery capacity. I've told you already we need to leave a certain amount of lithium in the cathode, otherwise the cell will collapse. So they're saying the usable capacity is 95 kilowatt hours. There's probably a little bit more in here again, but you just can't get access to that. It'll kill the pack. The cathode is nickel, cobalt, aluminium. The pack configuration is 110 in series and 72 in parallel. Nominal voltage 407 volts. The automotive cells, so we're just going to touch on some of the cells that go into packs and kind of who's using them. So that Model S uses the 18650 cell. We look at that. We can make it a thicker diameter of 21, thicker again of 46 millimeters, taller at 70 millimeters, or taller again at 90 millimeters. Then we talk about pouch cells, we talk about prismatic, and BYD, the Chinese manufacturer, has gone to cell to pack. And we will just briefly touch on these. So our 18650 cell, 65 millimeters tall, 18 millimeters thick. Just to note some of the numbers here. So at the very bottom, I'm telling you that's a 3.4 amp hour cell. When I do some rough math on this, the volume of the cell is about 14 cubic centimeters. When I do some calculations on the area of the electrodes, it's about, the length of the separator is about 1 meter. The width of it is about 60 something millimeters. The active area is going to be that 60 multiplied by 1. We have about 600 square centimeters is the active area of the electrodes here, which is either a lot or a little, depending on what you're thinking. It's a lot compared to some things. It's very small compared to, say, a capacitor. The 21700 is the same thing. 70 tall, 21 wide, about 5 amp hours from Panasonic. It's got about 21 cubic centimeters, a length of separator 1.4 meters, and an active area of about 900 square centimeters. And then the 4680, which I think is the cell in the Cybertruck, is 70 tall, or 4680. That's must be 40. It must be 80. No, that should be 80 tall. And that is a volume of 118 centimeters cubed, a length of 6.8 meters, an active area of about 5,000 centimeters, and about 24 amp hours is what's in there. That's the cell to pack technology. So what BYD are saying is, oops, we'll go back. What BYD are saying, yes, it's wonderful to have 8,000 cells, but it's a waste of space, and how about we optimize things better and we move away from these nickel technologies. And so what they have argued for and developed, and you will also find this technology on the Teslas and other vehicles, is it's so basically this is a prismatic cell. If I make this prismatic cell super long, so basically I do a big jelly roll and just wind them back and forth and make it really long, big long electrode, all in one piece, so I'm not creating subcells. BYD have perfected a whole chunk of that technology. So each of these is a single cell, where Tesla might have had many cells before. And in here, they've got 86.4 kilowatt hours. It's a LFP, lithium iron phosphate. It's 200S 1P, 200 cells in series, one in parallel. Prismatic is called the BYD blade. They're warranting this for 200,000 kilometers or 8 years. We can talk about that. 800-fold architecture. Nominally, yeah, lithium-ion technology. So just put some numbers on this for dimensions for what we're seeing. So let's go on to right here. We have the graphite on the anode. That is going to be bonded on to copper. So the green here is copper. Then we have our SEI layer. We're going to have our electrolyte, where if it all filled with liquid electrolyte. And then we're going to have the cathode. We're going to have aluminium layer. But what we're going to do is we're going to double coat each of these foils. So these are very thin foils. For my numbers here, the aluminum foil is about 8 microns thick. The copper foil might be about 5 microns thick. Separator is about 17 microns thick. The cathode coating, in this case, I'm showing about 90 microns. The anode coating is about 100 microns, very, very thin layers. So we're looking at across this at about just over 0.2 of a millimeter is the thickness of each cell. And I say we're double coating the foils. So that was our structure. So now I talked about the challenge we have with supercharging the battery. So we'll just start here, just an interesting slide that I kind of formed based on something I've seen years ago. Here, what we call the float voltage, just the maximum voltage we're going to put across the cell. Over here is the number of charge-discharge cycles that the cell can withstand before it degrades by about 20%. And over here is the stated charge. So we'll go to, we typically like to standardize on 1,000 charge-discharge cells. And that can happen with a max voltage, a float voltage of about 4.2 volts. And that will be 100% state of charge. I can move more lithium into the anode, push up the stated charge to almost 120%, increase the voltage to about 4.3 volts, but the number of cycles I can withstand is about 300 cycles. I've significantly damaged the lifetime of the pack. So if we're typically then, we know that the lifetime, the number of cycles we can withstand is going to increase as we push down this voltage, but the only catch is we also reduce the state of charge that can be moved within the cell. So, but things have moved on and are quite impressive, but this is where we certainly were once. When I first started this work, I would have good conversations in Detroit on some of these cells. And basically, if we said we could handle 1,000 cells, sorry, over here in the y-axis, we have the number of charge-discharge cycles, fully charged and fully discharged. Let's say our baseline is 1,000 cells, and therefore we discharge it 100%. Then the simple thing was, well, what if I only discharge it 50%? Then we'd get 2,000 cycles. If I discharge it 10%, we'd get 10,000 cycles. And there was a view that it had a constant energy throughput. So the less I do, the more cycles I get. Talking to the folk in Detroit many years ago, they're saying, no, we're far better than that. Maybe it's 1,000 cells at 100% state of discharge, but if we go to 80% depth of discharge, we could probably get 2,000 cells. If we go to 50% depth of discharge, we can probably get about 8,000 cells, discharge cycles. So now we're into great territory because there's only so many charge-discharge cycles we can impose on with our vehicles. And I've been using for this edition that I've introduced this other curve that we couldn't be looking at a baseline of about 3,000 charge-discharge cycles at 100% depth of discharge. And we're kind of working with that number. There's a company in Galway called Zerotech. I haven't been there. I know of them. Where what I really appreciate, they got some really nice specs. And they on their cells and on their packs. And here we see here, this is the Zerotech Hibernian pack. They got a 21700 cell, and they're showing here that the capacity of the cell dropped to about 83% at 2,000 cycles. They were extrapolating maybe that they would be able to, at 4,000 cycles, still be above 80%. But that's a pretty phenomenal number there, 2,000 cycles. Because if I put it this way, if I fully discharge the pack and fully recharge it every day for the next 10 years, that's 3,650 cycles. It's not a big number. So we're into big numbers now. I was in Germany doing some version of this in September, and the Mercedes folks were there, and their specs on their e-Actus, this is their 18-wheeler, their large heavy truck, is they're putting on 600 usable kilowatt hours, 621 kilowatt hours gross. They're saying there's a 500 kilometer range, 1.2 kilowatt hours per kilometer used. It's an LFP pack. They're providing a 10-year warranty, and a 10-year lifetime, designed for 10-year life, and 1.2 million kilometer service life is what it's designed for. The warranty they're providing though is 6 years or 720,000 kilometers. And over that, it will retain 80% of its data charge. And we can play with those numbers to back out what the real lifetime is. And they will say we'll do a recharge from 20 to 80% in about 30 minutes. 60% of the pack is 360 kilowatt hours. So to do that in half an hour is 720 kilowatts. So when we need our battery to last, we need it to be able to handle charge-discharge cycles. The deeper we discharge it, that will reduce the lifetime. When we specify lifetime, that can be years, but in our world, it is warranty years and it is kilometers. So the spec on the typical will be maybe 8 years and 160,000 kilometers. There will be variation in pack parameters, capacity and resistance, and those will degrade over the life of the battery. And we talk about beginning of life and end of life. Typically, end of life these days, we talk about 80% of the beginning of life parameters for capacity. Why does it age? It's going to age because the electrodes are going to expand and crack. We're moving a metal back and forth. It might only be moving 100 micrometers, but it's moving from cathode to anode and filling in and finding gaps in there, and it's going to cause some expansion and contraction with every time it moves. We're going to get peeling and cracking of electrodes, especially the graphite on the electrode. It's just like the lead in a pencil. We're going to get a decomposition of the electrolyte in the binder that's holding it all together. These are all hydrocarbons. We're going to get corrosion of the conductors, and we're going to get manufacturing defects. We will get growth of the SEI layer. We'll get reduction of the active electrode area. We're going to get a loss of active lithium. We're going to get a loss of porosity. and that's all going to result in increased resistance and decreased capacity of the cell. These are all caused by high temperature, high state of charge, high voltage, overcharging, low temperature, high current, lithium plating, high cycles, and high depth of discharge. All these things are acting to kill the pack. So every time you do that wonderful high power charge up the Midlands, you are working to degrade the quality of your pack. Low power discharge are better in mild temperatures. So this is a great one here, my safety slide. No, there's a nice video here actually where BYD show they drive a nail into their pack, and they show it just fizzles out, and they drive their nail into an NMC pack and it goes kaboom. And we're just about to answer why it goes kaboom. So here, so our thermal runaway, what happens? Our pack is designed to operate roughly your battery between reasonably minus 30 and plus 60. Now we'll show that it's not great at minus 30. But what happens at about 90 to 100 degrees or maybe lower is the solid electrolyte interface, that lithium barrier layer along the anode is going to break down. It's going to break down and react with the electrolyte, and we're going to get ethylene gas released, we're going to get methane released, and we're going to get propylene. All of these are hydrocarbons. And Edison would have told you at Ford that those are great to burn. So that's happening very early on. One of the things here is we're going to go as the exothermic reaction, we're going to go into thermal runaway. So everything is going to heat up. We're going to start melting the separator. And once we melt the separator, which is a polyolefin, which is also a hydrocarbon, we are going to get shorting from anode to cathode. So exothermic temperature is building up. We have gases, we have heat. At about 200 degrees, the electrolyte really starts to break down, and that we're going to get increased release of flammable gases. Now for that nickel, manganese, cobalt, somewhere over 200 degrees, that's going to break down. And the secret of that is that has the O2 in there. So now we release oxygen to meet up with the heat and the combustible gases, and we will get fire and explosions. And the big benefit that LFP, lithium iron phosphate, has is this is the equation for this iron phosphate, the PO4. That's a relatively strong bond between the metal and the oxygen, and it's a higher temperature before it breaks down and releases the oxygen. So that's why LFP tends to be a safer cell than the nickel-based cells. So Ted O'Riordan at UCC probably won't mind me mentioning him. Ted is a great driver of electric cars. He installed solar a couple of years ago at his home. He was working fabulous. Somebody gave him some used batteries from a data center somewhere locally. So he gladly took them and installed them in his shed and used them to recharge from a solar system. And this past August, it was a kind of hot day. I think somebody in the kitchen noticed that there was a sparking and arcing and a lot of noise outside and smoke starting to come out, and his nickel pack had gone on fire. Basically, heat, probably being overcharged, and given that we have all these caveats in here, was the wrong battery and the wrong application. That's why in our home applications, we're using LFP. So in a car business, what can possibly go wrong? Well, we can penetrate the pack. We get a straight head-on-head collision, easily done. We can crush the pack. Any of these, remember that polymer separator is only about 17 microns thick. It can be crushed in a heartbeat. The thermal stability can run away. To deal with this, we have thermal and fire barriers. We need to prevent against overcharge and over discharge. We need to protect against external shorts. We need to be able to allow these gases to vent from the pack and stop them building up. So all these are part of our pack technologies. This is a BMS in the pack. We tend to have fuses, we've got contactors, we've got pre-charge functions. We tend to have a manual service disconnect. We've got current sensors, and we have a battery pack monitor that is checking for failure mechanisms, high voltage isolation, high voltage interlocks, voltage, current, temperature, any faults coming in. It's got to be able to communicate fast and slow on the vehicle, and it's got to control the close of contactors and switches, and heating and cooling. So we see this in the next research schematic. So in our Chevy Volt pack, we got a coolant loop, liquid cooling loop, bringing that can heat or cool the pack. So we got heater and we got a coolant mechanism in there. This is where the main terminal is, where the contactors and the main fusing are. Each of these is the battery module. The yellow bars are bus bars. We have to be able to remove isolate the pack, say for a technician to work on or a mechanic. And so there's a manual service disconnect there that we can remove to service the pack. And then this is the battery pack monitor in there that's taking all the information in and trying to optimize the pack and keep it safe. Other parameters, we have significant max charge and discharge in an automotive, significant max, that's continuous. Then we have got peak. We have to protect against short circuits. That comes down to fusing and other factors. We've got to be careful about charge voltages or charge temperatures. Typically, we don't like to charge sub-zero because that can cause the dendrites to form and the lithium to build up on the anode. And we may need an accelerometer in the separately in the pack, just in case we have a crash condition, and we can ask the contactors to open if there is a crash. Just briefly on charging. So where's charge here? So let's go to state of charge. So that's the dashed line here. When we're fully discharged, we have a 0% state of charge. We're going to start pumping in the solid line as the current. We'll start pumping in full current, and we see the state of charge is going to rise. The voltage of the pack is going to, or the battery is going to rise to about 2.5 volts. And then what we don't want is, we don't want the voltage applied to the cell to go above about 4.2 volts. So we're going to taper off the current, and we're going to get a slower charge as we put the final charge into the cell. So for this reason, we cannot do high power charge of a battery to 100% state of charge. We typically have to scale back at maybe 80% state of charge and let the onboard charger take over. We see this here. This is downloaded on the Toyota BZ4 on a high power charger, again from the EV database. They were pumping in about 140 kilowatts. They were able to do that till about 30% state of charge, and then they linearly reduced it to about 85% state of charge. And then they're probably heading down, and eventually we will only be able to put low kilowatts in to take us up to the final 100% state of charge. So that's why when we pull up to a charger, if we're already highly charged, we cannot pull full power in there. We cannot handle the heat. We'll have tens of kilowatts going into that pack, so it cannot be done. We're probably, if we're putting in 100 kilowatts, we could have 10 to 20 kilowatt heat alone we generate in the pack. So it all comes down to, can the cooling system remove that heat, and up to a certain, it can initially, and then as the pack starts to overheat, it has to scale back and want to dumping in there. Just on resistance, this was interesting because, so if you remember last January, 12 months, there was a big freeze in Chicago, and all kind of complaints that folks couldn't charge, and folks couldn't, if they were discharged, either wouldn't charge. So a couple of factors here. There's a resistance we have in there. I just note here we have different resistances. There's a resistance of the electrolyte. When the electrolyte freezes, that resistance will go up. There's a resistance between the electrode and the electrolyte. That's going to be impacted by temperature. Collectors, not as much. So anyway, we always show in our simplest model a resistance here. When we're discharging, we drop voltage across it, but when we're charging, we pump in voltage. So this is, okay, this is slightly complicated. Let's look down at the table here. No, let's look at the graph. Let's go to the, so at 20 degrees C, the resistance on my pack looks like it's about 120 milliohms, 0.12 of an ohm. So all the current has to go through that 0.12 of an ohm. At minus 30 degrees C, that goes up roughly a factor of 10. And now I have a big problem. I've got a huge resistance there. Not only that, that seems like a huge resistance. But as we discharge, so here we're fully charged, depth of discharge is 0. As we discharge it, the resistance is heading up exponentially. So now if we're significantly discharged and it's colder than hell, or that's the wrong term, colder than somewhere anyway, this resistance is going to be very high. So if I go back to the problem I had here, if we're charging and this resistance is super high, to get a little bit of current in there, I'm going to get a very high voltage. But I can't let this voltage go above 4.2 volts because I'm going to damage the life of the cell. I can't pump high current in there because it's so cold. I'm also going to get lithium plating and the resistance. So I need to gently heat it up to drop the resistance. Now, I'll show you an example of that in a moment. So I need to simply raise the temperature of the pack and put in current with time. But a lot of what we put in initially is simply to raise the heat. This is we just show here the voltage from the, oops, and we go back here. The voltage of the pack, 20 degrees, we go from about 4.1 volts down to about 2.5 at 100% state of charge. But that resistance at -20 can be so large that I'll only get, say, 3.5 volts out, and at 2.5 volts, I'll maybe get to 70%. I'm not getting the capacity. I'm at a very low current here. But I'll show you now in the next slide. Again, the Zerotech stuff is great. Zerotech are showing here a discharge of the pack at 40 degrees, 25 degrees, 0 degrees, -10 degrees in red, and -20 degrees in blue. So the pack resistance is really high. But we notice here, right? You notice this, that the amp hours, the amount of capacity, initially it looks like we're really bad in voltage, but the voltage improves and increases, and then we get more amp hours than we would expect. We didn't get there with this one, but the reason that is happening is this. This is the same from Zerotech again, our folks in Galway. When I was doing a 3C discharge of this pack, so this is, say, a 5 amp pack, if I pull 15 amps out of this cell, the temperature of that cell internally rose 50 degrees. So when I was at -20 or -30, in reality, within minutes, it eventually got up to a very high temperature. And that's why we see it there. As it seems like we're getting the full capacity, no matter what we do in terms of temperature or capacity. That's because the temperature of the pack is increasing, even if the ambient is very, very low. So we're almost there. Last couple of slides. Sourcing. I discovered the other night that this is a thornier topic than I was planning, but we have civil engineers here, so they might be more familiar than I am. Two big ways of getting lithium. There was one in the news today. There's been a discovery in Arkansas in the US, and I think they got 10 years of global lithium supply. And that is all lithium that's contained in brine inland, in the basic underland sea in Arkansas. That they will, what to do is, so this is typically has happened in South America, Bolivia, is I suppose the brine is kind of flushed up with regular water, if that's correct. And then it is, the water is evaporated in the sun, and we're left with a mix of concentrated lithium brine that can then be processed to get lithium carbonate, and that then can be processed to get our cathode powder for lithium. The other option is our ore. So our typical ore right now is likely coming from Western Australia. There might be a couple of % of lithium in this ore that is dug out in Western Australia, trucked to somewhere on the coast, put on a big ship, and all the rock is taken off to China. So that's their lithium ore. That's what we call the mineral there is concentrated spodumene, and that ends up in lithium hydroxide. And that then the lithium comes out that can go into our cathode. I was given this talk, or a version of it, to the school teachers. We had some school teachers there from Wicklow, and there's a lot of controversy in Wicklow about mining in the hills there. I guess Canadian and Chinese companies have active mining licenses to look for lithium in the Wicklow Mountains, and it's causing a lot of controversy. I hadn't expected that. I must look into it a small bit more. As for disposal, when we started this business first, all the batteries were being made in Korea. I was at some, that global energy agency, whatever they call themselves. I went to talk. I was talking about this. There was an expert there from Belgium, and at that point, the packs were going for incineration in Belgium. But we're kind of moving on from there to recycling. There's a nice video from Volkswagen, which we're not going to play here. So basically, we need to very cautiously discharge the pack. Then we kind of disassemble it, take it apart, get the easy metals. Then we're going to take the cells themselves. We're going to grind them up into granulate. We're going to sieve them, and we've separated them into the metals and the cathode and the anode components. That's the approach. It needs probably significant economies of scale, but we are getting a significant number of batteries out there. And that, to my knowledge, is the end of this talk. Just to note here, there's a whole bunch of videos and references that you can reference. I'll just briefly note them. How batteries work, what CATL are doing to make a battery, a little bit more on cathode materials. This is the BYD. Watch the nail into the pack. It's kind of nice. It only takes a couple of seconds. The Volkswagen on the battery, reuse and recycling. If you're interested in cars or buying a car, the EV database is a fabulous website. And the US EPA website of fueleconomy.gov has got fabulous information. So with that, I've told you as much as I can tell you about batteries tonight.